Yeah, well, yeah, this is the fun stuff where when the CAD doesn't work, right? Because, we did something wrong, and then you get to figure out what happened and how you fix it. So,
Oh yeah, absolutely. I've heard some stories of smoke plumes, but I don't know the details. So I'm hoping to hear some smoke
yeah,
plume
we
details.
yeah, we've had relatively little smoke, so that's been exciting.
That's good.
Right, a few
Oh,
smoke booms.
I literally thought the white smoke was just a figure of speech, like not a real thing. And when we were in Minnesota, the hardware team's just like, oh no, Steve, like it's actual smoke will come up if
Yeah,
something goes wrong.
you thought it was like choosing the Pope?
Yeah, I thought it was sort of like the old magic smoke.
So, Steve, do you want to kick us off maybe because you may have obviously this is a first bring up for you and a lot of education. What was your perception going in, and you want to lead us off here?
Yeah, sure. Maybe just very briefly, because I think I, like Adam and like everyone, is very, very excited to hear kind of from Nathaniel's perspective, the coming into this and the stages and where things have ended up so far. But yeah, definitely my first bring up. My second real foray into being this close to the hardware. The first being the hardware hacking course that we took. I don't know, December 2019, and I think what I came away. So we went out to our manufacturing facility in Minnesota when we got the first boards off the line, and Nathaniel and Eric and Aaron and Ari and RFK and a bunch of folks were there, and I was there basically just to make sure everyone had coffee and get water refilled, smuggle water into the lab, and was uh, expecting that. Sadly, I expected that bring up of a board, if things went well, would all take place within like a day.
And I did. I mean, you didn't get that from me, did you? Did I say that? I mean,
I may have
Yeah.
contributed to this a little bit of like telling stories about bring ups that actually happened in a day, but also with the caveat of that was with an experienced team on like the fourth generation of the
well,
product.
and also, Rick, we did have a proto board that we are the proto board for the service processor running Hubris, which we brought up about a year ago, which was a day. I mean, we just brought that thing up, and at the time, Rick was telling anyone who would listen, like, do not infer anything from this experience. Like, this is not supposed to go this smoothly, and when we have bigger boards, it will get rockier. But maybe you missed the memo on that one, Steve.
Definitely. I honestly, when I was thinking day, I in my head was like even maybe a couple of hours. And so, there was one moment that will be burned into my memory forever, which was, the whole team is kind of standing over and sorry, after this, like, I think we want to go back to the beginning and walk through this, but we were at the point of applying 54-volt load and like testing whether obviously the first stage of power would come on. And in my mind, I think with all the buildup and all the time going back from the design into actually having a real physical artifact in our hands and then applying power, I kind of felt like it was this big milestone moment. And when that was applied and no magic smoke showed up, I remember like raising my hands and like maybe yelling, like very, very excited. And everyone turned their heads like, what are you doing? Like, this is like the first of 24 heats.
Right.
That's going to take like weeks.
This is like the first pitch of the game. And
Yeah.
you have just exploded in the jubilation that a strike has been thrown.
Basically.
Now, Steve, do you remember what day that was? Because it's all kind of a blur to me.
That was day 3.
Okay.
But we got there at night on Monday, so I think it was Wednesday.
Okay, yeah. So we had spent like probably parts of 2 days going through and just doing power checkout and making sure that the resistors we intended to put on were there and the resistors we didn't intend to put on were not there. Those kinds of things, right?
Well, and Nathaniel, this is actually an important point because you also, in doing that, in checking all the resistors and checking all the caps, you got the issues that you found in that.
Sure. Yeah. I mean, there were a couple of parts that, we intended to know stuff, which means, not don't install. And we messed up the property or messed up the BOM when we shipped it to our vendor. And so those parts got installed. And, you also do standard things like power plane checkouts. You want to make sure your power and ground planes aren't shorted together. And so we found a couple of surprisingly low resistance values between some of the planes. And so there was a little bit of a freak out about that. And we, sent one of the boards back for X-ray to make sure that, the part that, interacted with those two planes wasn't shorted, and it wasn't. And we had some help from Cliff and Rick, back in other parts of the country, beeping out some of their test hardware, which had the same kinds of chips on there, to prove that, yeah, some of these chips really just have low powered off resistance. And I mean, powered off stuff is like, there's no data sheet for powered off parts. So you kind of don't know what you're getting.
And Nathaniel, is it worth? Can you step back a minute and maybe talk about this board and what's on it, and what we're talking about here?
Yeah, so this is our server board. So we've got an AMD. We're targeting an SP3 socket family part. So we're going to go with the Milan silicon. It's got a bunch of. It's got 10 PCIe by4 SEM connectors, which will go to the front for our U.2 hard drives. It's got a bunch of DIMMs on it. So I think we can sit 16 DIMMs on there. And then we have, our control plane stuff. So like our totally not a BMC, as Steve likes to say. And so that's our, H7 ARM processor and our root of trust. And we have a 100 gig NIC chip down there on the board. So this is all on one monolithic board. And then all of the power supplies and everything that goes with that. So.
And then one, I think, important property for this is that there's not a traditional power supply on this board. So this is plugging directly into a DC bus bar at 54 volts.
Right. No AC.
All right. So yeah, you want to take it. So we spend basically more or less 2 days not powering, just doing all of your pre-power checkout.
Yep. Yeah. So Aaron and Robert Keith did a lot of the beeping out, but there's only so much you can kind of do. And then, as we go through that, we're doing some schematic comparisons too, and catching, there were a few already known bugs with the board. So we already knew some parts had to be swapped. And so we're trying to coordinate rework with our manufacturing partner to get some of the parts that we don't want to necessarily have to solder on the bench replaced, especially these multi-phase power supplies have huge inductors. And the inductors are really not fun to do in a bench setup. So you'd rather have them go, use some of their big equipment and take care of that. And so we knew those values were wrong going out there. So we had reels of new parts, but we had to have those swapped over. Our manufacturer noticed that, there were some Samtec connectors that don't have a clear pin 1 indication. And so they had been installed backwards. So, we had a bunch of stuff that we had to kind of coordinate with them to get flipped back around before we did power up.
And when you're saying beeping out, you were referring to that very reassuring beep that one gets from a digital multimeter when you are testing for resistance and you have connectivity, I assume.
Yes. Yeah. If you turn that feature on, right. Yeah. So, I mean, sometimes we might talk about beeping it out even without the beep, because sometimes the beeps get annoying. But yeah, we're looking at, resistance between, whatever two conductors you're looking at that point. And where you expect to hear the beep is where you expect to have low resistance.
So then you get to the moment that Steve has led us up to, that Steve believes is going to be, we're going to turn on 54 volts and walk away from this thing.
Yep.
And so you take us through that initial power.
Okay. So we had a Chroma bench supply there. Eric, who's on the call, had a lot of that set up. And we hit the power button on the bench supply and it current faults. And so that's, probably expected. We were pretty conservative with our current settings, but when you're bringing up a new board, you always want to have a power supply that's current limited, because something might go wrong and you don't want to melt things. And so you use a current limited supply. It turned out, after we went through a little more troubleshooting, the current limit on the Chroma was just way too low. And so, you slowly increase that until you can get over You know, a lot of times on a blank board, you've got a lot of inrush as the capacitors charge up, and we have a bunch of capacitors on the 54 volt side. So you get the 54 volts up, and so at that point we want to check, you know, all of the 54 volt supply. We want to make sure that what we call our IBC, so that's our 54 to 12, the big converter that kind of deals with most of the rest of the stuff, is off at that point. We want to make sure he's off and happy. We want to look at any derived power from the 54 volts and make sure that those are all solid. And so, you know, that stuff all checked out really well.
And Nathaniel, just on the current limiter, just to make sure, as a dumb software guy, I understand. Basically, you're saying if something is shorted and you don't have a current limiter, then the board is just a smoking pile. Is that right?
Yeah, I mean, the board becomes the fuse, and so
Okay.
wherever the trace is small, right, you'll either heat it up or it will blow as a fuse, and then now you've broken something you didn't intend to break.
Got it. Cool.
And then Matt, I saw you're here. I know you were diligently asking us for our bring up updates, and I was kind of deferring you to next week for a while. So I'm glad that you're here. You can get get it live here.
Oh yeah, Brian. Thanks for letting me in on this. I am really curious. I was looking at the photos posted by Nathaniel earlier today here. There's this big no man's land in between the front and back half of the board.
Yes. What goes into no man's land, Nathaniel?
Yeah, so we have a double stack of fans that sit right there.
Oh,
the fans are connected to the chassis. Those are also important to keep, you know, the server cool and everything. From a like electrical design perspective, they're kind of annoying because they're like right in the middle of where you might like to put stuff, and they take up most of the vertical space in the chassis. So we have basically nothing on top stuffed in that area, so that the whole chassis there are three sets of double stack fans.
Yeah, 3 sets of dual rotor.
That sit there.
Yeah, 80 millimeter fans. Those things can move a lot of air,
and they are very loud. Yeah. And then we have a shroud that goes over the CPU heatsink and the DDR, you know, slots and all of that, and blows air. So.
Yeah. So, sorry, Eric, go ahead.
No, more conventionally, like they'd be in the back, but then because of the fact that we're using a cabled backplane, those connectors take up some vertical space, so we'd have to use smaller fans if we went in the back of the chassis. And so it was a trade-off of board space versus available like cross-sectional area of a fan. And the bigger your fans are, the easier it is to run them a little slower and still get plenty of air moving through them.
Yeah, in fact, actually, the big change we had to make with these fans is they actually default to their lowest PWM, being 5,000 RPM, which is super loud still. So we actually had them modify the fans down to 2,000 RPM so they can run a little quieter.
Yeah. And hopefully last a little longer. Because if you're not running them at the utter hairy edge, hopefully they'll not smoke their bearings too quickly.
And so being in the middle of the chassis, does that present replaceability issues or?
So, I mean, for better or worse, those are actually the easiest things to get out. So when you're in a chassis, the fans kind of drop down from the top, and they and then there are connectors on the board, and so you got to pop 3 connectors kind of back near that black heatsink in the picture, and then the whole chassis that holds all the fans together just essentially lifts out after you take a couple of screws out the side.
And so we, as you may infer, we made the deliberate design decision to not make those fans hot pluggable for a bunch of reasons that we can get into. But you've got to pull the sled out to replace the fans. And we've got what we called the 3-up design, where that whole fan apparatus comes out as one piece, and you replace it with a new one. So with the logic being, if one of those fans has failed, the other 2 are going to be due. All right, so Nathaniel, you want to take us? So we've got this thing. We don't have smoke pouring out. Steve has
no smoke.
Steve has done a Jersey slide strangely through the Bringup lab. Everyone looking at him awkwardly now.
Yeah, so we have a really small ICE40 FPGA in that power domain, and so it has some derivative supplies that deals with some of the very low level like presence detect and link management stuff. And so that guy had to be programmed. Of course, that's where you start running into some of our first problems where, we had a schematic issue where the SPI signals were swapped around, and so then that means we got to hop in there and pull some resistors off and put some wires on and that kind of thing, to get the dongle talking to, or to get it to so that it could talk to flash and configure itself.
And that was, as I recall, like that was a very quick issue to debug.
Oh yeah, that was pretty easy because we have a header there to talk, and so we could talk to the flash part, or I think in reality we could talk to the FPGA and not the flash part, and so it was pretty clear to figure out what direction was swapped, and then once you have that, you program the flash part and off you go.
And this is one of 2 FPGAs that we've got.
Correct.
And so
yep, that's a little tiny ICE 40. That it's 1,000 LE part basically, and then we have an 8K ICE 40 that does a lot of our power sequencing, which we'll probably talk about a little bit later.
Yeah, we'll get to them later. All right, so we figured that out pretty quickly, and the ignition I feel got programmed pretty quickly.
Yeah, once the dongle was talking, then it was up, and Aryan had a design kind of ready to go so that we could turn the thing on and off on the bench, which is what we wanted to do. And yeah, so that was all good. And so then you move to that controls the IBC, right? So the IBC is our 54 to 12 volt converter, and that becomes like the power for basically everything else on the board. At that point, they all derive off of that 12 volts from the IBC. And so prove that the IBC works, I think we had to add a pull down or something because he was a little unhappy when the FPGA was configuring, little, issues like that. But then 12 volts is up. And so then we start looking at all of the supply rails again that are on by default when 12 volts is up. And so, you kind of like rinse, lather, repeat on the voltage bring up and go through your schematic and check all the things. So no big issues there that I remember. And then you're kind of at a point where it's like, okay, we're ready to start messing with our embedded control plane, right? So it's time to program the service processor. And that went super smoothly. That was, like you connect the dongle and like we had a target built for that. You and Cliff had worked on that, and it was very smooth. And, we had our Hubris OS running there, just kind of like snap your fingers.
It was great. Now, I confess, maybe I was doing the Jersey slide at this point because we are now only a couple days in and things are going really smooth. This is great. Like
right.
We've got,
yeah.
It's like we've got the SP up, and now we're beginning with the service processor up now, and us being able, like now from a software perspective, like we're in business. Now we can begin doing all of our checkouts on all of our I2C buses and everything else.
Right. And as a hardware guy, it was awesome to be able to have like an embedded target and an OS and a bunch of code that we had already proved out on various dev boards, and maybe just needed a little bit of a different pin configuration or whatever for this board, but really getting up and being able to run pretty quick. That I spent a lot of time that day after getting the SP programmed, going through and doing I2C bus scans and PM bus scans and that kind of thing to make sure that all the devices that we think we can talk to are all like sitting on the network at the addresses that we intended. That turned out to not be the case generally, and so there was a lot of rework too. There was a late, maybe not a late breaking change, but there was a spec change at some point in the project that never made it into the schematics. And so a bunch of the addresses hadn't actually been updated in the BOM. And so we had a bunch of swapping to do on that kind of stuff. But that's all pretty easy rework. A lot of it is just resistor straps, and you just change them and off you go.
Well, so this I thought was actually an interesting little design intersection that where we deliberately did the rework required to bring the board in line with the spec rather than changing the spec. Which I thought was, I thought that was an interesting. I guess maybe that wasn't even a decision from your perspective, but I guess I thought it was interesting that was a clear direction to go.
Yeah, I guess I didn't really consider it an option to not.
There was good for you.
There was a lot of thought put into the addresses that we had chosen, and so and then I know certainly I think philosophically our team doesn't like implementation driving specification. and just for the convenience of it. And so, flipping things around to match the spec really made sense. In general, I would say there was one somewhere in the, craziness of getting this stuff swapped around. We did interchange 2 of the power supplies addresses. And by the time we figured that out, we already had a number of boards reworked. And so that one was a spec revision because, but it was a little different than picking just a new device out of thin air. It was just 2 parts that had, swapped their addresses.
And then importantly, changing the specification in that case and making sure that what we don't want to have is a bunch of different snowflakes that have got different parts of different addresses.
Right. Yeah. And so like Eric and I, worked at a different company, for a lot of our career. And like, this is one of the key things as you bring up multiple units is to make sure that they all have a clear life cycle and a clear indication of what they are, and they should all match in general. And so, that's something we both feel really strongly about. And so we had, written an RFD on that process before Bringup to make sure we call them model change notices, but essentially you build an atomic change and then document that as a change, and then the boards get relabeled with those changes and you move forward. But then anybody can look at a board and say, okay, I know that this has had this number of changes to it.
Yeah,
this is the
it's such a great process. And then the other thing that I thought you guys also brought in terms of like bringing engineering culture is just the documentation of everything that was being done as we were doing it was tremendous.
Yeah, that worked out better than I think any of us could have imagined. I mean, we invited Aaron to come, and he kind of lived less as like the guy with the soldering iron and more as the guy with the keyboard. And so he sat there and just took copious amounts of documentation and notes of all of the changes. And I mean, really, that was more documentation probably than even we had ever experienced anywhere else. As part of Bringup, just because we were able to like put a person in the seat and that was his job, and Aaron did an awesome job at that.
That's funny, I could have assumed that you guys had always done it that way because it felt so natural. It seems like such a good idea.
It really does, and I mean, after having done it, I'm sure we'll get to more of it, but like that really has paid dividends.
Yeah.
And so I don't see us not doing that ever again. I think it's totally worth one more person sitting there just focused on documenting. And then I think that's helpful too as a company where like the whole team can't really come down to the lab because not everybody was on site, and like really not everyone is ever on site for any Bringup, since we have people kind of spread all across the country. Being able to like clearly document that stuff in a way where the rest of the team can follow along and be appraised of the changes and understand what's going on and ask questions, I think has been really valuable.
It's been really valuable. And I think that, a point that, we are not a documentation first culture to be a remote friendly culture, but boy, those two things definitely go hand in hand.
Yep.
And really, so no, you're totally right. Okay, so we've got the SPs up. We're going through these I2C buses, making some minor mods, but things are looking pretty good.
Things are, yeah, and we're starting to like approach the period where like things that we have previously integrated, like all the software and everything, we're sort of running out of the like things that we know work, right? And so at a certain point, you and Cliff hop on a plane to head out because we've been trying to get the FPGA that's sitting there involved, so that like I'm responsible for some of that and like getting the SP to program that. And so I think Cliff was hacking that driver on the plane as he flew out to Minnesota for us. But we had found a couple more schematic problems there where we had multiple things sharing a SPI bus, and so there was some bus contention, so we had to have some parts ripped off, and so managing that with our manufacturing partner.
Yeah, and I think that speaking from my perspective, and I think Cliff's too, I mean, indeed, the entire company, like you really just don't want the code that you're delivering to be in the hot seat. You know what I mean? It's like, please God, don't let it be me that we're blocked on. So we're just trying to like, how can I just need to stay like a block ahead of the parade here. And we were doing that a bunch.
Yeah, I mean, I think there were a lot of jokes about the Eye of Sauron and who it was pointing at any one point in
That's
time,
right.
right?
I know. I know.
mean,
And I think it's to a certain degree, like on it, like we are such a team-oriented team that nobody wants to let the team down. So it's like the Eye of Sauron ends up being like much worse. I feel.
right. Yeah, so we had a few other things to do, and then you guys had landed, and we made it there, and we're trying. And Cliff had done a lot of awesome work to get the FPGA loaded. So we've got FPGA loading, we got spy traffic kind of running back and forth between them. We can communicate some new drivers and that kind of thing, all hacked out, and then it's like, okay, we're ready to like start exercising the sequencer. And so that's, this is all stuff that we have now really not been able to test up until this point, right? We haven't had the hardware. We don't have things that handshake like the sequence does.
So you should describe what the sequencer is. Like, what is sequencing? Why is this a problem?
So generally, AMD has a fairly complicated power on sequence. So there are, I don't know, somewhere around 12 or 13 rails that go into the AMD chip. And they kind of all want to be brought up in a certain order. And then, as you look at, like, take a step back, the DIMMs have, 3 or 4 rails coming into them, and they want to be powered on and off in a certain order. And you want that stuff to be sort of deterministic. And so, a decision that was made a while back was to push a lot of that into the FPGA there that sits there. We call it the sequencer. And so essentially the SP, says start sequencing. And then the FPGA logic runs off and turns a bunch of things on. And there are some checkpoints with the software at various, spots along that way to make sure that things are working. And you bring up all of the rails for the DIMMs and the AMD processor.
And where does the sequencer get its bit stream from?
So the sequencer, at the very beginning, we put it in a flash, and then we realized the flash and the SP and the sequencer were all contending on the same bus. And so Cliff did some cool work, and we pushed that into the SP's flash image, and we just ripped the flash parts off the board. So we had our manufacturing partner run around and pop off a couple of the BGA flash parts, and we did one there on the bench with a hot air gun, which this board, it's an 18-layer board, and every other layer is ground. And so getting this thing warm enough to pull stuff off easily when you're trying to pull like a BGA off is a real pain.
Yeah, so tell me about that board heater, because the board heater, I unfortunately, I didn't get a chance to watch that thing run, but everyone was just marveling at the board heater.
Yeah, so our manufacturing partner had a little Pace, maybe kilowatt heater or kilowatt and a half maybe. And you put that underneath and you put the board in a rack on top, and you let that guy run. And so he heats up the bottom of the board. And what you're trying to get the thermal mass of the board to get up close to reflow temperature, so that then when you hit it with the hot air gun, you just kind of like slowly crest across the the temperature that makes the solder turn go from solid to liquid.
Yeah, for like non-hardware people, imagine a toaster oven with a convection feature, and you literally flip it on its back, open the door, and then put a board on top of it. That's basically what the board preheater is.
It's like a little space heater almost.
Yeah, it's convection oven with a hole in it.
And and reflow temperature, this is the temperature of the solder, at which point the solder is effectively liquid.
Right. Yeah. So it's somewhere up in the like 250C range. It kind of depends on what kind of solder you're using, but for lead-free stuff, up around 250C. And so, but you want to kind of heat the board up to like 150 maybe. You don't want to melt all your plastic, but you want to make it so that your hot air gun just has to do a little bit of a push to get across and turn everything liquid. And so we did one of those there on the bench with, and that was, as much fun as that was, we didn't want to do the other 12 like that. So we, or the other 11. So we sent the other 11 back to, we had, our manufacturing partner who we were at, they could run them through their big BGA rework station and pull all those off pretty easy. So we had them go do that for us.
And I think this is a really neat little change of the bit stream being in the SP image itself, because it means the attestation of the SP image automatically attests this bit stream that we're going to dynamically load onto the FPGA.
Right. Yeah. You also avoid a whole class of errors where like one thing got updated and not the other, and you have to figure that out.
You also avoid
then,
manufacturing issues with the flash part goes obsolete and you have to qualify another one,
right.
and there's limited parts that work. And
yeah, and I mean, finding flash has not been a problem this year, right? So
yeah, right.
Yeah.
No supply chain issues.
So I mean, the cool thing is we freed up that part, so we have a bunch more flash parts. We use that part in a couple other places on the board, so we have a bunch more inventory than we maybe intended to have.
Well, I thought we were
And
going to
then-
just resell those parts in lieu of doing our next raise. I assumed we were just
right there you go.
some flash gray market activity.
Right.
Yeah, no, as far as you know.
And I mean, since then, Cliff has done some cool work to, to compress the bit stream even nicer on that thing, and then decompress it on the fly, so it takes even less flash than it did while we were there in Minnesota 2 months ago.
Can we stop for a moment, just from a software perspective, to praise include bytes? This is what Adam, the include byte. Have you used include bytes or include stir, the macro?
I've
Adam?
used include stir, but I haven't used include bytes.
So include bytes is just the logical equivalent. So those of you, I mean, this is like a religious experience, I feel, with Rust, to discover include bytes and include stir, take a file off the file system and drop it in effectively into your file as a string or as bytes, which is great for an FPGA bit string, right? So pretty neat.
Yeah, very cool.
So I am curious, how are you guys planning to attest the FPGA image before doing this?
Well, so we will, in terms of like, how do we attest that the blue spec that we are generating is that that bit stream has not been tampered with, or what do you mean?
Right. So, I mean, I can see how you can attest to the software image that then loads the SP, which then loads the FPGA. How are you planning to do that before you made it load in that sequence? Or were you just not attesting the FPGA?
So I mean, we're not currently attesting the FPGA for development, and the plan always, I think, was to do this, but we had the flash part on there kind of as a fallback in case, we didn't have the software there in time, or we didn't want to deal with that right now.
Okay, so this is just bring up magic.
Yeah, this is just bring up magic.
Okay.
And I mean, it's always cooler when you get what you hope your product solution is as kind of the earliest thing too. But when you're like throwing hardware down in the schematic, you're just never sure where you're going to land. And like I said, like that driver was essentially written on the plane as Cliff flew out, and so it worked pretty well for plane code. Right?
Cliff writes great plane code, I gotta say. I've been in.
Right.
I mean, certainly much better than my own aircraft code. Like his plane code's pretty great. All right, so we now have the sequencer. So now we're going through, because I'm trying to think of the things we were trying to do before we powered on SP3, which is the actual AMD socket.
Right. So as we went through sequencing, we found a few different problems. I mean, sometimes the net names maybe were called out active low, and the parts were actually active high, and so like the FPGA bit stream had to be kind of flipped around a little bit. So we did kind of a bunch of that, and then like as we're going through this, we get to the level translator issue. Do you remember that?
Are we going to talk about the blown inductor first? I feel like the thing that we did.
Yeah, that's true.
I got to think we're going to talk about zombie board. Eric, are you going to talk about zombie board and the blown inductor?
So yeah, somewhere along the way, after we got the embedded stuff up and running, we sort of had enough of the board risk retired where we were willing to like risk more boards, and so we started bringing on a second and third board, right? And so once we had a second and third board, we could pass one of the boards off to Eric, who does a lot of our power stuff. And so he started looking at, with the AMD has a fake processor load called DSCLE. And so he started looking at some of that and some of the other power supply designs. So maybe he wants to talk a little bit about how Zombie Board was created.
Well, hold on, Nathaniel, just to see if I understood that correctly. So early on, you only have a limited number of bullets here, so we conserve them and move very slowly, it sounds like. But then when we gain a little bit of confidence, then we're able to parallelize. Is that right?
Yeah, so it's kind of like if you have a bent socket, you don't want to stick a bunch of pins in there, and then every back in the days when processors actually had pins, if you had a damaged socket, you wouldn't want to run all your processors through there because you could accidentally damage all of them. And so, until we got to a certain point, we really were single threaded on a single piece of hardware doing all of the rework on that guy to make him happy and to prove that, like, we didn't have some major oops that was, going to melt parts or ruin other things. And so by the time we got to like the SP up and running, it's kind of like, okay, we have enough stuff here. We have the power supplies up, everything's being controlled. We have varying amounts of rework on certain things, but we kind of understand all of that. So let's go execute that rework on a board 2 and a board 3, which were kind of coming off the line hot from our manufacturing partner too.
Nice.
So because they had done flying probe, which requires some development once you have hardware. And so we got our first unit, but without having gone through flying probe.
Nathaniel, just a little plug for Flying Probe. Flying Probe is so cool for those who.
It is cool.
Yeah, so maybe just a little explanation of Flying Probe.
Yeah, so it's an automated DMM basically, and
DMM digital multimeter. Sorry.
Yes, right. Yes. So it has robotic arms on the top and bottom.
I couldn't hear what you said. Sorry.
Oh, that's
Could you say that again?
Siri. Thanks, Siri. It has robotic arms that move, on the top and the bottom, and it has spring pins. And so it moves down and touches electrical contacts on your board, or moves up from the bottom. And you can test continuity. So they take your net list in, which is like all of the electrical nodes on your schematic, and they figure out what they can hit with those probes. And then they program the machine up to go through, and it uses your CAD, and it goes through and checks continuity in those areas, and it can do some limited like resistor measurements and capacitor measurements and that kind of thing.
And videos of this are mesmerizing, so definitely go watch videos of this.
Yeah, and it has they have a limited number of probes, so it's not like a bed of nails where everything gets tested concurrently, and so it just moves around, and they're fun. There are a lot of good YouTube videos about that.
Okay, so you've got these boards that come off hot. Sorry, yeah.
No, Nathaniel, sorry. Just one other thing that I wanted to mention is that we skipped ahead of, but to the uninitiated, one of the things that was fascinating for me was in that first stage of Bringup, I think it was like a FLIR camera app that Arian had that we were using to detect when parts were starting to warm up, which indicated life.
Right.
And
or death.
Or death. And that was again back to the those in the bleachers with popcorn. That was pretty fascinating to watch the test and being able to see parts kind of come up live on that thermal camera.
Yeah, especially when that's a common trick. As you bring parts up, put a thermal camera on there. Maybe some people have seen resistors get really hot in certain power circuits, not on this board, but in other boards, and it can teach you a lot about what you messed up in your design for essentially free. And so I have a Seek thermal that connects to my camera, and Arian had FLIR, and so putting those on, and you could watch, especially when you start bringing the power stages on, which as we get to Zombie Board, we'll certainly talk about that, because Zombie Board definitely did get some thermal shots dropped into the chat channel. For sure.
It definitely did. So Eric, with that entree, do you want to talk about Zombie Board?
Yeah. So before we put the AMD load simulator, the SDLE in there, I wanted to get these processor power supplies up and running even without that, just in case it sent 12 volts at them, because I don't want to blow up our one load pod, because they're hard to get. And so I hardwired the feedback back to the controllers and turned things on, and it seemed to be kind of working. But there was a bug in the schematic where there was a recommendation that wasn't followed on one of the current sense signals going to the power stages. And to give you an idea, like the core of this power supply, when you're doing this testing, can pull north of 250 amps at a volt or so during testing. I mean, they don't do that in normal life usually unless it's a surge, but that's what we test to. And so this particular error caused the current feedback from these power stages to be bad, and that caused the controller to kind of lose its mind. And this is an 8-phase power supply, so there's 8 of these stages, the 8 of these switching supplies, each of which can theoretically put out 90 amps. You never use them that high, but it caused one of them to go bonkers, and it sent 12 volts right at the output. And one of the things that you do on these low voltage power supplies is you never really put high voltage rated parts on there. So the first big capacitor that it hits after it goes through this power stage is a 4-volt rated aluminum polymer cap. And at 12 volts, that thing becomes a lovely resistor. And it it got a little toasty, which I found out by accidentally touching it after the thing started going crazy. I'm like, what the hell? And I touched it. Geez, what the hell? So we turn it off, bring the thermal camera over, turn it back on, and there's this glowing red death right at the bottom. It's like, oh, that's not good. So
I do find that's usually the sign to bring the thermal camera out, is when somebody burns themselves on something.
Yeah, that's
God's own thermal camera.
Nathaniel's comment on a resistor is there was another board that we had designed that had a random resistor on a FPGA that was just smoking hot and barely not desoldering itself. We found that using a thermal camera, a little tiny 0402 thing that was like 150C. But yeah, so Zombie Board basically committed suicide at that point, but luckily our rework person was awesome and she was able to pull that power stage off, put another one on, and I tried firing it back up, but the 12 volts had damaged all the caps. I was hoping it hadn't, but I had to rip off all those caps and replace them. And once that happened, and we got that one problem with the current sense fixed, then it fired up much nicer after that.
Yeah, and I just want to make clear, because Adam, the Nathaniel and Eric both mentioned this, but they may have gone past it quickly. This SDLE that we're using is this really important piece of equipment that AMD makes that is a load generator. So go ahead, Eric. Yeah. Describe SDLE, because SDLE is really pretty cool.
Yeah. So instead of retail high-end Milan processor being like $5,000 or whatever, instead of just throwing a Milan in there and praying to whatever God you want to that it doesn't immolate into a ball of fire, you put this fancy load pod on there, and basically what it is a bunch of electronic resistors. They use MOSFETs, and it abuses your power supplies in a controlled manner and watches how they respond. And there are limits to what it will allow. So like it'll do a load step from, let's say, 50 amps to 200 amps, and the voltage that it does that to can't change by more than a couple of percent of its voltage. So if you have like a 1 volt rail and you do a 150 amp load step, it can't change by more than, let's say, 10 millivolts or 20 millivolts, and that's like 1 or 2%.
And does this thing give you some readout or diagnostic or some report card of how you did?
Yes.
Yeah, it's pretty slick. Like they built it not MATLAB. It's Simulink. No, God damn it, what is it?
LabVIEW.
LabVIEw. Thank you.
LabVIEw.
So they built it in LabVIEw, and it's executable, and it connects to this thing. And it's pretty fancy, but it spits out basically a giant CSV, and they have some Excel spreadsheets with macros in them that digest that and spit out some nice graphs that show you like your minimum maximum voltages, the voltage versus frequency, and this load step it doesn't just do it once, it does it repeatedly for like a second at a time, and it does it anywhere from like a kilohertz up to like 300 kilohertz. And so it'll just slam this thing, and you can actually, if you're in a quiet room, you can hear it going through the different frequencies in their audio range because the magnetics start humming.
And
that sounds really cool.
It is really cool. And also this thing is speaking. So AMD has a protocol between the actual CPU and the controller. And so this thing called SVI2. So this thing is speaking over that protocol and verifying that it's getting the right answer back. So which is really, really neat because it allows you to actually completely check this out before actually loading up a real CPU on there.
Yeah, so it's completely invaluable. Intel has the same thing for their stuff, and there are commercial companies that make independent ones that are like Load Slammer, and Intel has their own version of Load Slammers, and it's kind of standard fare for high power, high-end stuff where you can't afford to use chips to test it. It's also used a lot with like ASIC Bringup because you only have a few Rev 0 ASICs, so you want to make sure your power supplies are very well behaved before you put that very first silicon into a board.
This sounds a little bit, Brian, like what we talked about last week with the switch and the Tofino 2 like physical sample part for testing kind of physical characteristics.
Yeah, absolutely. And in fact, Eric, one of Eric actually mentioned load slammer. We have for Tofino 2, one of the first things we did is got a load slammer for that part. So we're going to be able to do the same thing when we do the sidecar bring up.
Cool.
Yeah, that thing makes AMD's power requirements look trivial.
Yeah. So all right. So so we've got actually the point we didn't think it was zombie board. We thought it was dead board, and then when it came back, we realized that it was going to be
alive again.
It was alive again.
Yep. It couldn't die.
Yeah, that was like we're sitting at dinner that night. So this was a Saturday, I believe, and we're sitting there at dinner, and so I texted our manufacturing partner and just asked, what are the chances that we could have a rework person come in on Sunday, because we're going to be back doing this, and this is one of the 2 or 3 boards that we have access to at this point. And so they managed to get their high-end rework person back in there on a Sunday morning and did the work for us. So, and then we were able to get this board back in our hands, and it still functioned, albeit with some quirks, which are fine.
Yeah, we super glued the socket cover back onto that one so nobody accidentally puts a processor in it. But the nice thing is, once we got that one problem figured out, like the 2 biggest power supplies, the core power supply for the AMD and the SoC, which is like the hidden processor power supply, both those passed the SDLE testing with flying colors. Both those are just fan-friggin-tastic. It was great.
And we may come back to those later.
And those, yeah, the other rails had some quirks and whatever, but at least the 2 big ones, power-wise, they worked fabulously.
All right, so we are now getting ready. We've got Zombie Board, and it's now. I think we are now getting ready to actually attempt our first SP3 power on. I think at this point, right?
Yes, yeah. So this is probably now Thursday of the 2nd week, right? And we've got a processor loaded in there, and we're gonna try to power this thing up. In fact, did we actually put a processor in there? We must have.
Yeah, I think we put them or a ROM.
ROM. We had a ROM processor in there. Okay.
And then because it was the level shifting issue on when we first attempted we should describe the level shifting issue, because that was definitely another major hiccup.
I'm trying to remember if SDLE was still connected or not, but regardless, so there's a level shifter there. Well, we have a lot of level shifters. There's an I2C level shifter on there, and to I guess give the answer before the walk up, that guy was misbehaving, but we didn't know that at the time. And so what we saw as we're going through some of this stuff is we're seeing like I2C transfers not work, and a bunch of really strange things. And so we've got our Saliers connected to the bus, and we're looking at, this is like the Eye of Sauron then points back at Brian, because his I2C thing it's his PM bus thing is pulling bus reset like on loop. And, we're like, what in the world, And so, anyway, we're all looking around.
The Eye of Sauron is going googly-eyed at this point. Yeah, Eye of Sauron, exactly. It just seems to be going everywhere.
Because we thought like we'd load a different FPGA and we get different behavior, even though the FPGA doesn't even sit on that I2C bus. And so we're building FPGAs with like all the pins tri-stated and all the pins high and all the pins low, trying to figure out what is causing this. And the FPGA is somehow related to this problem. And so as we got through it, we started binary searching basically on the FPGA pins, turning them all high and all low.
And Nathaniel, I think there's also a very important detail that led us down the wrong path on this. This appeared to only be happening on one of the boards.
Right.
Which it turns out was a total accident. Like, as it turns out, both boards, we were basically in undefined behavior effectively. And maybe you want to define a little bit what a level shifter is and why they're so problematic.
Well, so level shifters, especially on a bidirectional bus like I squared C, are especially tricky, right? So a level shifter in general just takes one voltage from low to high or high to low, depending on what you're trying to do. The problem is when you have a bidirectional bus like an I squared C bus, the circuit has to be able to do high to low and low to high and figure out which direction it needs to do, and kind of like these things end up all being kind of magic. And really they're not. I mean, you can go in and figure out how these parts work, but it turns out that the part that we had chosen here did not have defined behavior on both sides of it when one side was powered down. And so one board worked a certain way and the other board worked a different way when they were both in the same state where one of the two sides was powered down. And to compound matters, of course, when we put our Salier on, we're sitting on one side of the bus, and that's the side that is powered and things are working. And the SP is sitting on the other side of the bus, which is the side that wasn't, or maybe vice versa. But like what we were looking at on the analyzer was not actually what our processor was seeing, because this level translator was, kind of acting like a mirror basically, and you couldn't actually see what was going on behind the mirror.
I think the Eye of Sauron was burning a hole in my brain at that particular moment, because that definitely looked like this is like the SP is doing something, is misbehaving with respect to I squared C, is what that looked like.
Right. So
and in some regards,
and this was also where we were digging through data sheets trying to understand, how does this level shifter actually work? Like, what are we missing detail wise? And the level shifter is offered by two manufacturers. They make the same device, but they offer compatible parts. And one of the data sheets tells you absolutely nothing about how it works. The other one tells you just enough that implies that you understand how it works. But until you notice that they actually have links to YouTube videos illustrating how it operates, that's the only place that they actually describe how the part works.
Well, and it turns out that with these same level shifters, we had a different level shifter problem once we got back home as well. But like it all hinges around, these things don't really have defined behavior when they're powered off.
The ones we picked. So, there are devices.
Yeah, the ones we picked.
That,
there are ones that do. Yes.
But with hashtag supply chain issues, makes it more of a pain to find nice supply, nice.
They may have been the ones that were available.
They may have been. But it was, it was an interesting object lesson in a lot of different ways. I mean, one, I feel like, these kinds of I squared C level shifters.
Brian, I think we just lost
Brian. Yep, we did.
The level shifters got him.
Yeah,
pretty much.
Powered off. Yeah, those things, they're for things that should be, seemingly are very simple in your circuit. They end up being a very complicated in practice, and you really do have to go through and make sure that you understand how these things work.
Well,
and
it also depends.
And as Rick said, like some of the data sheets are not helpful. Like you read every page of the data sheet and you have no idea how the thing actually works. So.
And we picked this particular component because we could source it, or because it was compatible with different things?
Yes.
Yes. And you like every one of the translators has some quirk, and so you're just like, we were using this in other places, and its specs are good enough for the data rates we're looking at, and we could source it, and so that's how we kind of ended up with these. And if you pick a different family, then you just get a different set of issues.
Gotcha. So you just fire up those YouTube videos and learn about the spec.
Yeah.
Well, gotcha.
So shout out to TI. TI has a much better data sheet on these parts.
Yeah.
So of course it's TI.
But
this is the most TI thing I've ever heard.
Right. Well, their data sheets are much better than
YouTube videos.
Nexperia's.
Yeah, Nexperia's
yes,
terrible.
But they're also notorious for putting that one footnote that you really cared about, like on page 364 behind the door marked "Beware of Jaguar."
Yeah.
Right.
But actually,
the note is there.
This issue was clear in retrospect, but at the moment, in some regards, like the scariest moment for me was when you, Cliff, Eric, and RFK all had a look of total what the fuck is going on? Like
Right.
fear, like actual fear in all four of your eyes. And I'm like, okay, I am terrified. If these four are scared, I'm wetting my pants because you've got engineers that are pretty fearless engineers with different perspectives on things. And when everybody has no fucking idea.
Well, and yeah, because we discovered it while playing with the FPGA, but the FPGA doesn't sit on the bus. That was the part I think that we could pretty conclusively prove it was the FPGA was doing something, but how that interacted with us, and I mean, it turns out the FPGA was controlling the power to the thing, right? And so, once you figure that out, it becomes a lot more obvious. And but yeah, up until that point, we're like, the FPGA is not even sitting on that bus. How can it be, messing up that I2C bus?
I mean, it literally is like I'm turning on and off the lights in Houston, and Atlanta
Yes.
is bursting into flames, and I do not
Exactly.
understand how these things could possibly be related.
Right.
But so we get through that, that was a good moment, and now it feels like let's go power this thing on.
Right.
Let's go.
Yeah.
Then what?
Well, let's see. I'm trying to remember.
We did it the next morning.
What happened?
Because
Yeah,
that was late. So we broke up late that night. We're going to come back the next morning. Cliff and I have got flights out the day after. We're going to power on SP3. It's all going to work. It's going to be amazing. And it does not work. We come back out and we roll we actually populate the SP3 socket. Because I think I want to say Friday morning was the first time we tried to do that once we had that issue resolved. But maybe I've got the timing wrong.
Yeah, I think we were getting ready to head out.
Yes.
I was packing up the mobile lab back into the minivan.
Right. and
it just nothing really happened, right?
Nothing really happened. And so and what are we looking for is kind of the first sign of life out of the CPU. Nathaniel, you want to describe that?
Yeah, we're looking for spy wiggles, right? So the way these processors boot, you do some handshaking, and then kind of like they boot out of like an on-chip ROM basically and execute some code. Their PSP does, and then in fairly short order, they're going to go out the SPI interface the way we have this strapped and attempt to fetch code, and so we had wires tacked onto that SPI interface, and nothing is going on, nothing's dumping out the UART, and we're running out of time really there in Minnesota.
Running out of time, and all right, can't get it working. You and Eric are going to take the boards back to Wisconsin. We also decide to send you with all of the Milans and a bunch of DRAM. The cargo of the minivan was worth much more than the minivan.
Yeah, because this is a rental town and country. So that's not even that expensive.
Right,
so.
Right. And then you've also got the SDLE. So the SDLE being the irreplaceable.
Right.
And
so you had instructions for us.
I did, right. If carjacked, give them the DRAM and the Milan CPUs. Do not part with the SDLE.
You can hack these easy on eBay. They're unlocked. You'll have no problem unloading these. Just please, for the love of God, don't touch these 4 boxes. They are worth nothing to you. You can't sell them, and they're worth everything. Please,
they are priceless. Right. We only have one SDLE. Fortunately, no carjacking, no problems.
Right. No pirates.
Gotcha. No pirates. No piracy. You're right.
Safe at home. With
safe at home.
All the equipment.
But
yeah.
Go ahead. No, sorry. Yeah.
I was just gonna say. So then we start the okay, now what, right? And so we have a board, and so it's we must have done something wrong sequencing. And so let's go read AMD's documents, and so we get a board set up here on my bench, and I rework a bunch of wires onto it. And I mean, Eric and I spent a couple of weeks in my home lab here, doing various testing. I mean, lots and lots of testing. Check power supplies. We wire out all the sequencing stuff. We the first time we try it, we get the whole team on a call late at night one night, and watch nothing happen.
Nothing happened.
Essentially. And
I know,
then
at this point, like, Steve has been wounded so many times that he's just like, all right. But Steve is so enthusiastically enjoying it. It's like, no, nothing's happening.
Right.
All right.
And so then I feel like, another few days go by and we find some more things and we fix some more things. And, it's like, then we do another call and a bunch of people, from the team join. We get on there and we show it. And this time, it's not nothing that happens, but like we're playing with Power Navigator, which is the software that's driving the power controllers. And so I've got that's like a sideband in addition to our SP control.
Sitting on the same I2C bus the SP is.
Yeah. Yeah, and it's got a dongle, like USB dongle, and it's mastering I2C, but it's polling and doing a lot of traffic. And as we're talking through it, I think the suggestion comes out to do an I2C bus scan.
God, who made that suggestion? That is negligent. Right. I mean, that is obviously the wrong thing to do. I mean, boy, blameless postmortem, but
right.
I need some names.
Right.
Okay.
So Brian suggests we do an I2C scan, and so we do, and like the instant I execute that command, like everything in Power Navigator goes from green to red, and errors just fly up, and it's like
Power Navigator turns out gets really, really unhappy if it can't scan things.
It did not. It was very upset.
And probably there was probably some bus resetting going on because like the SP, thought it should be the master.
And the SP is accessing every single address on the I2C bus, and so that may or may not have caused things that are undefined in Power Navigator land to go bonkers.
It was bad.
It was not great. And so like at this point we're like, oh, we probably killed the processor. Lots of things.
Oh,
and
at this point, I think one of the rail set was reporting at like 80 amps on the SoC rail.
It shouldn't. Yeah. Oh, this is one of the DRAM controllers.
Oh, it's
MEM.
That one.
Yeah, it's not 80. It doesn't draw 80 amps.
Oh yeah, the memory controller with no DIMMs on that side. Yep.
I think and I think Keith's telling us like what the datasheet spec is, and it's like spec to pull like 20 amps or something, and we're seeing 84 in the diagnostics, and it's like, oh, this is really not great.
This is bad. So just like a quick aside though, because this is actually an interesting artifact of the kind of the new way of working with everyone remote. We recorded every one of these kind of like these rolling out of to the pad of SP3. We recorded. And it was actually really helpful to go back and rewatch what we did and be able to see exactly what we did when.
Yeah, and you can get time correlation there too, right? So it's like you can see when I hit enter, and like within the next like quarter second, everything went bad, right?
It was bad.
We could rewatch that moment again and again. Hey, try this. Hey, try this.
I am happy to report that processor is actually fine. So
which is amazing.
Out.
We thought we had killed the processor.
Yeah.
And
we were convinced.
And apparently we haven't. And certainly that thing had experienced some abuse. I mean, that's the first one, and so like some of the sequencing wasn't perfect, and mistakes were made all along the way, but that guy does seem fine. So
what did you guys actually do when? What did you guys actually do when you scanned it? Was that like set all voltage rails to minimum or turn them off, or
no? When we were scanning it. And honestly, like it's actually still a little bit unclear why. What is more likely, honestly, is that we were initiating bus transactions at the same time the Power Navigator was initiating bus transactions, and it was just getting back nonsense because it was seeing our traffic and wasn't handling it very well. I mean, I2C is definitely not a multi-master bus, right? So it is that they are.
Not at the same time. Yeah,
definitely not at the same time. Exactly.
Well, and Power Navigator, when it doesn't get like responses, it starts reinitiating the power supplies, and it'll start reloading their entire config over I2 and trying to restart them again because it's lost synchronization, I think it calls it. And so at that point you're like trying to burst traffic across I2C while the SP is trying to scan things, and the God knows what's happening on the power controllers, but the Power Navigator likes reinitializing everything because it assumes it's on a dev board or something, and it can do that.
As all good dev board software does.
Yes.
Right.
Yeah, right, exactly.
And of course, this is running, some Windows 95 looking
Oh,
GUI that you can't.
Yeah.
Actually,
That takes 10
I mean,
minutes
actually,
to figure out how to talk to something on I2. Yes.
That's the Renaissance one.
Yeah, but
Yeah,
to its credit, it has some really nice features that we are trying to shamelessly steal.
Yeah.
I would
They're
also
trying to
say,
emulate.
in the grand scheme of like vendor software,
It's pretty good.
that one's actually pretty nice.
Yeah,
It looks
it is.
decent, and it sort of works. I mean, there's certainly some other vendor software we have experienced that
Less kind.
I
than
don't
to
know
say
what
that.
it is.
Yeah, it doesn't work, or-
Every vendor's
Yeah.
PLL software, like to interface to their PLLs, is just a complete shit show.
Oh, come on. ADI is not that bad.
ADI, TI, they're all awful. Like, even if you have good, like, TI's power interface stuff, their fusion interface is not too bad at all, but, like, their PLL stuff is just terrible.
Well, and we are trying to load the EEPROM in the clock generator, and we were hitting, like, it's like unrecognized EEPROM type other. And I'm like, okay, obviously this is a misconfiguration. And you guys were all like, no, the software is this bad. I'm like, it can't be this bad. This doesn't work at all.
It is this bad.
Yeah,
you haven't been jaded enough.
No,
Right,
it was like a
yeah.
total like country mouse moment. We're like, no,
Well,
Cantrell, you idiot. It is this bad. Like, stop overthinking it.
I mean, to be fair, in this specific instance, like there is a button in that software that does not work.
Oh, yeah.
And
Yes.
but like we we're looking at it, and like after you play with it a little bit and don't see any bus wiggles or anything, it's like, oh, well, that button just doesn't work. And I guess we're like
That
all of us
button
hardware
calls
guys
no.
are too Stockholmed to like be that mad about it. It's
hang
like
on,
we're used to
only
this.
one, right?
Right.
No, that is it. That is. You're right. But that's basically it. I'm like, where's the indignation? It's like, we're just exhausted, man. Can we just
I fully expect there to be like 4 to 5 whole tabs of features that are not implemented.
Yeah,
Right.
and I think this actually just does drive to our whole zeitgeist, which is about getting fully documented parts and then being able to program these things without proprietary tools, and doing that. And to their credit, the vendors are not unsupportive of this approach. And I actually, one of the things I like about Power Navigator is broadly it is using PM Bus to communicate, and we can do the things that Eric likes about that tool. We can emulate in Humility and Hubris, which is pretty neat.
And we are on a lot of it, right?
Yeah.
So
PM Bus has always just terrified me insofar as you are letting software control the voltages that can explode your CPU.
Yep.
So interesting. There are ways of. So one of the things on like the core supplies, let's say on these processors, is you can do voltage margining where you can tweak over PM Bus. You can tweak the voltage up and down. But to your point, you can tweak the voltage up to 2 volts and just completely just melt down your processor.
Yeah.
But you can also configure it with a way that won't allow that, so you can't actually touch it over PM Bus. And so one of the things we're going to maybe eventually get to is being able to load these things over I2 with an attestable image, such that it won't let you, even if you got on that thing with fly wires and a bus pirate or something, you can't over voltage the thing or under voltage it. Now, if you get onto the AVS bus and start mucking with that, or the processor bus that tells it what to do, well then all bets are off. But at least from the PM Bus side, there are ways of preventing that at least. But yeah, you're right. It's scary as hell, especially because like the Renaissance parts are slick enough and fancy enough that you can tweak their control loop while they're running. And so you can do some very interesting things if you don't do that right.
Oh, that's not terrifying at all.
Yeah.
Yeah, right, exactly.
The TI parts make you turn them off first. The Renaissance ones are like, oh yeah, no problem. I can run that. I can do that as a running change.
Yeah, hold my beer while I do that.
Yeah.
I will say though, like, I think with our team's approach to software hardware co-design, I feel like there's a healthy concern in everybody who's interacting with this stuff to make sure that like we don't do dumb things like that. And so that's, I mean, I'm sure we'll make some mistakes, but like there seems to be like a lot of care and thought put into these things to make sure that they come out right. And so that's been very nice, I think. And the team is all very, aware of like the fact that like there's something physical also going on. It's not just bits running around in a processor.
Yeah, definitely. And for those that are curious, we open sourced Hubris and Humility last week, actually. So you can actually go look at the software that we're talking about and the software that does like PM bus reporting and so on. And definitely if you find bugs, let us know.
Right.
But because it is, yeah, it has consequence. Like if you get it wrong, you can break the thing.
But if you get it right, you have a lot of built-in diagnostics and
that's right.
parametrics that you can get out of it, which is amazing.
It's really cool. And so, all right, so we are now, I feel we enter the prolonged period of
now we're in the
state
of despair.
Eric living at my house.
Yeah. Eric living at your house, Valley of Despair. Matt, you asking us on the Twitter space, how's Bringup going? And I'm like, okay, end of Twitter space. See you next week, everybody.
And here we thought Brian was just running away from me the whole time.
No, exactly. No, it's like, please don't ask about Bringup. And you know, because we are double, triple, quadruple checking everything. We're going through.
Yeah.
I feel like there's this moment where, because understandably, and AMD is being super helpful through all of this. AMD is trying to help us brainstorm it. The only real symptom we have of this thing is it resets after 1.25 seconds.
Infinite reset
That's it.
loop.
Infinite reset loop.
Yeah, so it has a fancy handshake sequence, and so we go through all of that, right? We're all the way up to
and
like
everything
the
looks happy.
Theoretically,
everything's happy.
Like loading code out of its ROM. Everything seems happy, and it hangs out for a second and a quarter. We never see any spy wiggles, and then it just resets, and it's like reset, hang out, reset, hang out.
And so meanwhile, we're trying to get ours to work. Rick on the other side of the country has an Ethanol X that he's trying to get to break in the same way that ours is broken.
What's an Ethanol X?
Right. So
Ethanol X.
Ethanol X. Ethanol X is a reference system from AMD. So the CPU vendors, when they release a processor, typically make an entire motherboard and provide that to the OEMs as this is how we expect you to build it, and this way you have something to compare to when something doesn't work. You can at least see an example of a working system.
And I mean, like at this point, Rick's Ethanol has already had a significant amount of surgery. Because we've prototyped some things before we cut out, and then he's been instrumenting it to get sequencing samples so that we can compare against our own design.
I have no shame about taking a soldering iron to a very expensive motherboard. So yeah, there were many experiments where I was just totally willing to remove components and attach wires and do all sorts of things. So my board was in a good shape to use as this candidate for, okay, if we can't figure out why our board isn't working, can I modify my board to look as close as possible to our board and see if I can get it to fail in the same way?
It was incredibly valuable because what we discovered is Rick could not get this board to fail no matter what he did. And actually it was really important because there would be hypotheses about different signals that we don't have wired up or wired up differently than ethanol. And Rick would be able to validate, like, nope, that doesn't matter because I can hold that low and it still boots. I can do this to that and it still boots.
Despite what your documentation says, this doesn't matter.
Right. I mean, I think we should talk a little bit about KB Reset L.
Absolutely, KB Reset L. So explain KB Reset L.
So KB Reset L is, like something that our company generally hates, right? Because it's this like leftover vestige of like a keyboard reset. And so it's like a pin that maybe could make the processor reset. And, today that's all connected up to actual BMCs and that kind of thing in different designs. AMD suggested that in the documentation, it's like, if you're not using this, it'll internally pull up high. So float it. And so that's what our design did. We floated it. As we're going through the debugging, that was one of the things they suggested, like, can you confirm that KB Reset L is high? And so we're like, oh, sure, no problem. And so then, as we look at our board, though, we realize since it's floating, like the via from the socket to the back of the board has been stripped off. And so the only this connection, I don't know how people are familiar with the SP3 sockets, but SP3 sockets have little spring pins in them, and they reach up and touch little gold dots on the bottom of a processor. And those little spring pins are kind of like little tiny wires, and they're wired down to balls that are soldered onto the top of the board. And then, for signals that need to go elsewhere on the board, we have a via right next to that, and the signals fan out on internal layers. However, for signals that like KB Reset L that doesn't go anywhere, oftentimes the vias get removed as part of the CAD and layout process. So on this board, we have the spring pin soldered down to a ball on the top of the board that we can't really get to, and then it doesn't come out to a via in the back. And so Eric and I are sitting there trying to figure out how we might figure this out. And Eric's like, I think I can solder onto this thing. And so we have got pictures of this. It's pretty impressive work on Eric's part, but he stuck a 30 gauge or a 40 gauge magnet wire down, and we tacked underneath the bottom side of the spring pin under the socket and soldered onto that, and so we could wire that pin out and look at it, and then we could tie it high or low.
And you really need the dime for scale. Like if you
this
look at
is
it without the
very
dime,
tiny.
you're like, oh yeah, I don't know, that looks, is that small? And then you look at like, what is that massive star there? It's like, oh no, that's a dime. You're like, oh
Right.
God.
Yeah, I mean, the magnet wire is thicker than like human hair, right? But it's a lot thinner than even a 30 gauge rework wire. So yeah,
And is magnet wire like a standard tool in your tool belt? Like, did you have that hanging around?
Yes,
Okay.
absolutely. Everybody's got a spool of this stuff.
Yeah, and it's nice for this kind of stuff, or if you need to tack to traces. Like we use a lot of 30 gauge for like most of the rework, but like for really nasty things, the magnet wire is really awesome for that. So,
and we'll tweet out a photo of that because that's pretty mesmerizing. And so this is, and I'm thinking like, this is okay. I get it, gods. I hope you've enjoyed your little playtime. You have punished us by making KB Reset L, the fact that it's floating, the fact that we've got a pin in this microprocessor that has to do with the keyboard, which obviously this thing will never have. It's like, okay, we get it. Joke's over. Can we please boot now? Now we can boot. Nope.
No, that was not it.
That was not it.
Yeah. And meanwhile, we're running all these other experiments in my my board. I've managed to remove something like 40 components from the Ethanol X, and I just have this like growing pile of resistors and my board is still booting. Like that's the amazing part. It's like it's actually still working.
We can't do anything right. We can't even break a machine correctly. It's like Jesus Christ.
You ever seen Beverly Hills Cop? I think it's Beverly Hills Cop 3, where Eddie Murphy's driving this car out of a chop shop and parts are just falling off of it. And you just keep
right, exactly.
That's Rick's ethanol.
That's Rick's ethanol.
And parts falling off of it.
So I have to say, if I can just take it now, a quick aside to read an excerpt from this book I read on ENIAC, because boy, did I feel this. When things wouldn't work, frustrated workers referred to the machine as the maniac. Another of the engineers remembered joking that if they gave their drawings to the Germans, they would set back the war effort 10 years. We were young and deeply involved. We felt like the whole war program depended on us, Goldstein said. There was a real sense that we were doing something very extraordinary, which I felt like this thing is the maniac. Like, what is going on? And I also feel like we've got the total confidence that we're going to resolve it, but at the same time, total confusion about what's happening.
Yeah.
And AMD is being super helpful with this. Yes. I mean, AMD is like making all sorts of, they are like, boy, we have not really seen anything like this. And they're making a lot of suggestions and we're acting on all of them. This is where I think Nathaniel writing everything down was a real win.
Yeah, at this point, we have 136 pages of notes.
Right. Yeah. And so
this is also where you start to question reality, where you're like, okay, so clearly following the documentation didn't work. Trying to break our board or break our reference design didn't work. We're not getting any answers from the vendors because they're working hard on it, but nobody knows what is wrong with this thing, and running out of options as to what could possibly be wrong.
And
start getting into so what are the really wild things that I've encountered in past bring-ups that could possibly be wrong? And this is where we run into things like, yes, I have been on a bring up where it turned out that somebody's multimeter had not been calibrated and was in fact reading wrong. and that takes a really long time to figure out. Things like that, and just asking all these mundane questions of, okay, now we just have to really check what are we missing?
Something
Right.
obvious.
We're missing something.
And so Eric and I live like 20 minutes apart. And so every day Eric is showing up with a trunk full of more stuff. And so it's like, one day it's the SDLE, another day it's the Ethanol X, another day it's like, a Keithley DMM.
Two different DMMs.
Yeah, 2 scopes and, all kinds of stuff, just to try and like, zero in on whatever is going on here. And we've been instrumenting our part. Of course, like at some point in this process, like we drop a probe on a powered board and it toasts the board. And so then it's like, okay,
right.
Like this
as is
a
tradition.
bad day.
That was a Friday.
That was a bad day.
Friday at like 8:30 in the morning, and it's like, oh.
And we're going into the holiday week the next week, so we had a super small window. Yeah, that was like, oh,
and it's
man.
like, well, okay. I mean, that board had, like days of rework on it. And so it's like, well, because we have a whole bunch of stuff that we don't actually ever want to see again, but it's like brought out right now so we can get the scope captures that we need for sequencing. And so we, we shipped that one back to our vendor to have a BGA part replaced that blew up. And so we start round 2 on another board. And, I mean, like at a certain level, you're like, well, maybe there was just something wrong with that board.
Right. But it's had a spell cast on it. That makes sense.
But at the other side, you're like, now I've got to check everything else again, because I've got to, get back to that same place. And so we get back to that same place, over the weekend into Monday.
Well, and the thing that's also worth mentioning on some of these theories, and Rick, I'm sure you and Eric felt the same way. On some of these theories, you'd be like, okay, well, we're going to try it with this thing set the other way. But fuck it, this is it. It's going to be very distressing because it's going to mean that, this signal that's clearly documented to float, or this signal that's clearly documented to be one way, it magically needs to be the other way. It was almost like, I want this thing to boot, but not at the cost of my sanity, I don't think. But then I was like, you know what, I'll give out my sanity. Fine.
Right.
Well, there's always the, how painful is it going to be to fix this if we're right? Yeah. Because at this point, it's a significantly thick board. It's got all these, all this work that we're trying to do on it. If it turned out that we made a mistake on something that was an inner layer, like that starts to get into a very, very difficult to solve problem.
Yep. Well, and we did find, so before we blew up the board, we did find kind of a crappy layout on our OV9 supply to the core. And so I remember, one afternoon, Eric and I had found that, as the processor loaded, we could see the voltage fold back, and it was like, this rail has fairly tight specs on it. We're not meeting it. You go look at the layout, and the layout kind of got botched, and it was like, okay,
that's it.
This has got to be it, right?
That's got to be it.
We're getting under voltage,
and
so
the
we got
thing's
to call
dropping
with
like
everybody.
100 millivolts on a freaking 0.9 volt rail.
Right. And so we chatted with people, and it was like, okay, this is it. And so like a lot of good ideas, like we could steal voltage from some other supply on here. And Eric's like, no, I think I can just copper tape a new plane onto the bottom and fix it. And so he
was amazing, by the way.
Yeah, I mean, as a software guy seeing that, I'm like, really? That's what we're doing now? Okay, cool. That's awesome.
It was amazing, because also I felt like this fits all the evidence that we've got. This has got to be it. And Steve, you remember us talking at the office. I'm like, the good news is this is it. The bad news is it's not going to be reworkable. As it turns out, like both of those were wrong. Like it is reworkable, and it's not it.
And I mean, to be fair, like it only requires one layer of copper tape. Like we didn't have to put Kapton on and add a second layer or anything, So like in the grand scheme of rework, the SP pins were probably worse rework than this. But so Eric lays down a new copper plane, and we try it again, and of course now the supply is rock solid, and the board still reset loops.
And actually, it should be said that like our SDLE like report card, Adam, that you were asking about earlier, we have gone from like A's and B's to like A pluses. I mean,
Yes.
we are now like the margin on this thing is now to the point where AMD's like, wow, I've never actually seen power this good. Like this is amazingly good power. Like the margin
wow.
there is incredible.
Great.
Like
Thanks
wow,
for nothing. Right.
right, very impressive. It's like, okay, can you boot now? Like please
Right.
please boot. And then Eric, I'll walk you through the walk you up to your big breakthrough. But it was in part of those conversations with AMD where they're just like just throwing a bunch of stuff out about, check this, and they mentioned the SVI2 traffic and looking at just making like go back and kind of, and we'd already looked at that stuff and it hadn't been an issue.
Well,
And the power supply is responding to the commands from the processor.
And SVI2 is required to pass SDLE, and so like it's clearly working.
It's clearly working, and so it's like we're not like okay, but we know the SVI2 is working. And so Eric, maybe you can walk us through your thought process based on that. I mean, because that clearly like got you just digging deeper on that.
Yeah,
I mean, we were desperate.
Yeah, very desperate. But like one of the AMD folks just casually mentions like, oh yeah, I saw some support ticket or somebody mentioned that like, oh, if you don't see a VOTF in the right amount of time, that could cause a reset loop. And I'm like, the hell's VOTF? And so I go look at the SVI2 spec and I look at VOTF as the special. It's a special packet that gets sent by the power controller when, like, let's say a processor requests a voltage change. So like, let's say the load, the app load on the processor has really gone up and it really wants to, get tons of power really quick. It'll tell the voltage regulator, hey, I want, instead of 1.0 volts, I want 1.1 volts because I really.
And this is and VOTF is V in on the fly, right? I think it's
voltage
what VOTF
on the
stands
fly,
for.
and then the C is complete.
Right.
So it's an on the fly voltage change request from the processor. Could be up, could be down, whatever.
And that is sent successfully.
Yep, the processor says,
the command is
go to 1.1
the command
volts. I see the slew up to 1.1 volts. It's well controlled. There's no overshoot. There's no ringing. There's no nothing. It looks beautiful. And then I'm like, okay, well, what the hell? Like, is there anything in this tool that the SDLE runs on that measures something in here? And it's like, oh, okay, SVI2 measurements, whatever. And I'm like, wait, what the hell does this packet even say? And so I zoom in because it even has a utility to capture SVI2 packets, like with that transition. You can tell it to transition, it'll capture the traffic right after it. And I realized that it doesn't seem to be sending a VOTF packet. It just sends normal, like there's two single direct, it's like a SPI bus at like 3 megahertz or something. And so there's a data bus that comes from the processor to the controller, and then there's a telemetry bus that goes from the controller to the processor, where the processor is told, hey, your rail 1 is at 1.1 volts and your current is 38.7 amps and temperature is blah blah blah, and the processor uses that for something. And I realized that it's just sending normal like telemetry back. It's not sending the VOTF packet when it's supposed to be.
It's not sending the complete packet. It's not saying it's not responding with I've done this.
Yeah, it's not responding with the hey, I've finished, even though it had finished. And it was responding and sending telemetry and otherwise behaving normally.
Literally half the protocol.
Yeah.
It is implementing the half of the protocol that changes the voltage, but not the half the protocol that said I did it.
Yes. And so I sent an email to Renaissance FAE, who is awesome and responds very quickly with a, so if you try this different software and there's a little button that should be pressed in the GUI, and it's like, okay, I pushed that button, but all right, fine, I'll get this newer version and install it, and then ding, there's the VOTF complete. I'm like, what the?
So in the end, there was arguably from our perspective a bug, and actually from Andy's perspective a bug too, in that the SDLE was actually looking at the telemetry packets, but didn't actually note whether the complete packet had been sent or not.
Even though it easily has the capability of looking at that and really should be checking
that.
And a bug in the power tools that when you turn this feature on, it only turned half of it on.
It turned half of it on. We set that bit to 0.5.
So in the true spirit of Oxide, this turns out to be a firmware bug.
Yeah.
A hidden
God, it
firmware
is.
bug.
It is. I hate to say, I hate to be so on brand, but yes, it is.
Yeah.
And I mean, but to be clear, like everybody, honestly, in this is one of these things that, like, all of these folks were incredibly helpful in helping us get this problem resolved, and we're really grateful to Renaissance and AMD. And then importantly, like we get all of this, this FAE at Renaissance is just terrific and got us everything that we needed. Because I was worried that like we're gonna have to like get a new part.
Right.
Or we're going to have to like navigate some huge bureaucracy within Renaissance to find an answer to why this is happening, and they won't know, and it'll be like, oh God, now what? It's like we should have used this other part. This wasn't the part they used in the reference design.
None of that happened for them.
Oh no,
here it is.
Here's
Yeah,
how you do it.
and
No worries.
We get the new things programmed, and boom, spy wiggles.
We get spy wiggles, and then we
we noticed that the spy wiggles pins aren't quite right, and we have another
right.
Another little swap, but we have.
I feel it's kind of like the action movie that's like you think like the villain is dead, the movie's over. It's like, oh no, not quite over.
Right.
We got to do one more little rework.
Monty Python, not dead
exactly.
Yet. Just a flash.
But I mean,
moon.
that was real clear. Like we had, that board was ready with headers instrumented on the spy and everything, and so as soon as we saw spy wiggles, it was like super clear that like D0 and D1 are swapped.
My God,
and
damn it, we swapped SI and
like,
SO.
Oops. And so, a little trace cut and a little jumper and
magnet wire later, and
so.
And then
I think that was kind of the end of that day. I mean, so like, because I got that home and had to do some UART rework, or like, so we didn't bring the UART. We needed to bring UARTs out to a header so we could see them and some other stuff. And so that was, and then the next day we had a demo.
We had a demo, and we had a demo that was talk about the Eye of Sauron whipping to me, where so the first thing that's going to happen are these spy wiggles, where the PSP, which is this proprietary security core inside of the AMD part, it downloads its firmware. And then it's going to start booting the processor. And then the first thing we're going to see out of this thing is it attempting to train DRAM by asking where the DRAM is. And this is where it actually is going to hit our code. And Nathaniel gets everyone out. Let's get a demo. And then.
And so, and to be fair, like I knew we were going to land there because I had gotten there that night, the night before. But it was like, this is good because like we have characters coming out the UART from the SP3. And then in our design, our service processor sits as a proxy for the SPD EPROMs that are on all the DIMMs because we want access to those in our control plane. And so that's the code that Brian's talking about, where the AMD processor is going to go out and talk to our service processor and think he's talking to DIMMs, and we proxy all of that. And so it kind of zipped through and said none of the DIMMs are present.
Which, of course, like could be lots of different things. Fortunately, this is where I think the tooling and all the stuff we've done, we were very quickly able to determine that I had fucked up, and I had a cut and paste error from. I actually was looking. I'm like, I'm looking at my own code, being like, how is this fucked up? And Rick has realized like you cut and pasted it from Gimlet, not from Gemini.
Yeah, it was just a pinout problem. It wasn't even a logic problem.
No, it wasn't a lot of problems. So just pin problem, super easy fix. And then we came all the way up, except then we ended up with like Keith had left you an image that had a very dramatic hello world message, but now we had a Windows terminal problem such it could not give you the actual like glorified image properly. And now we're into like new unsolved problems of how to get PuTTY configured correctly with respect to line breaks.
Yeah, so we had to, you need the implicit carriage return on line feed or whatever. And so we got that done and, kind of cycle the whole thing over and get all the way up, and we see Hello World and Oxide's, nano bootloader that Keith's been working on.
And it was glorious. So we got all the way through.
That's running our x86 code, right? Which is kind of the important part of that. Because everything up until that point is kind of running AMD's blob of stuff that does all the DRAM. Like we don't get to control that. And so then, ta-da, we're running our code.
And it means the DIMM's trained and everything else. So we always long way to go, but definitely wind at the back. And Steve, you had said that you had a line relatively early in this of like, we're going to have a good story around the campfire when all this is done. I think you've just been at the campfire.
Well, Brian, you're forgetting that last little bit of the story. So we get to this wonderful point. You can see the output.
Yes,
it shows that we booted. And then you can't type anything.
The last part of the story. Oh my God, how can I forget this?
That's right. I will never forget this.
Right, and because like we are who we are, everyone's mind is immediately running to the absolute worst case scenario. So Keith is like, we are hitting, it's a therm trip, or we're like the CPU is shutting down, or we're
stuck. Yeah,
processors stuck.
So we get a terminal basically, right, with Keith's stuff, and so I should be able to issue characters, and no characters occur, and so it's like, okay, we kind of shut the demo down at this point, and I'm like, look, we'll go figure out what's wrong with the serial port. There are only 3 or 4 wires here. It can't be that hard, right? And so looking into it, and it's like we're using hardware handshaking because this is all up at 3 megabaud, and the pin that our FTDI dongle should set low to, or sorry, the pin, he should see the processor have set it low so that he can issue characters. It's high. It's floating high, and we can't issue characters. And so, we go through, and, if you've ever dug through FTDI data sheets, they're TX and RX, and like, I feel like every hardware and embedded guy in the world has had to deal with like who's TX and who's RX, and like which direction to all of these things go through all of that. Everything's fine. So I spent, the rest of the afternoon kind of chasing that. And I get to a spot where like I finally probe the board in such a way that I realize like, oh, my dongle isn't working. My FTDI chip is not doing what I'm expecting. And at that point I'm kind of like, okay, I'm putting the computer down. I'm going away. Like, this has been too much today.
Which is, I have to say, Nathaniel, you have such a high threshold for pain. When Nathaniel had the message in the channel being like, I am walking away from the computer for the day, you're like, okay, it's grim over there.
Now, the sad part is, of course, I go upstairs to watch TV or whatever, and all I can think about is why isn't this working?
The computer is like, you'll be back.
Yeah. So I come back down, and I'm like, I'm gonna like, and I had tried like 2 other FTDI mini modules, and like I was getting different behavior on each one, which is never inspiring confidence, both in like how you're testing it and like the product itself. And but and it's like, well, it's got to be something I'm doing. So I come back down, and I'm looking at this pin, and it's an input, and it's kind of floating high. And so I'm like, I'm just going to ground the pin with a little DuPont wire. And so I grab one of the DuPont wires, and I just like connect that pin to ground, and I measure it with my DMM, and one side is ground and the other side is floating. And I'm like, wait a minute, like this is not like electrically possible.
Right.
And so then I pull the DuPont wire off, and I ohm it out, and it's an open circuit. And it's like, right. And so then I'm like, okay, so that explains, part of what's going on here. But I'm like, but I have this other DuPont wire over here and so I ohm that one out, and it is also an open circuit. So,
so DuPont wire, we're talking, these are like the jumper wire that you have in like a breadboard, a maker breadboard. Yeah. This is like stuff that can't fail. Well, mostly.
I mean, it's so of the 7 DuPont wires that I had involved in this setup, 2 of them were open circuits, and 2 of them were open circuits, and like I'm like, they were broken or something, because or maybe like heavily oxidized, because like I pulled the plastic off to look, and it's like the copper is still crimped in the crimp, and they're open. And so that it happened to be, that was the pin, the RTS CTS pin was an open circuit. And so as soon as I got an actual wire there,
I know we said that, talk about a bullet whizzing over the ear. So that only, because that implied that flow control was constantly on, we couldn't TX. If that had been on another pin, we wouldn't have seen anything.
Yeah, right. We would have ended up back into like Salie land, putting specs on things.
Yeah, right, exactly.
And like,
we would have figured it out.
probably
we would have
figured that out pretty quick, because like we would have seen it wiggle. But it depends, because it depends on where you put the salier. Because if you put it at
Right.
the end of your broken wire, you're not going to see what you expect. So
yes, Rick, thank you very much for remembering the end of that. It's just, I mean, a broken DuPont wire at the end. So it's like busted firmware, broken DuPont wire, KB reset L. Like, gods, are you happy yet? Are the gods content at this point? Can we, Jesus Christ?
Well, like I said, we had already gotten to the point where we were questioning reality. We did it a little too early.
That's right.
It was.
So I can confirm that that entire set of DuPont wires has been scrapped. So we're not going to mess with those anymore.
There you go. Done with those. Well, it was a and Adam, I'm sorry. I know you've got Josh.
No, this has been killer. This has been killer.
But I feel like this is a story that had to be told. And I feel like also these are the stories that are frequently not told, honestly, because they kind of they're told kind of among engineers at a company or what have you, but they're not often told publicly. But this one was obviously and also Matt had been asking every week, so it's like we had to.
Gotta tell him something.
Gotta tell him something. Exactly. That's right. So, but this was a hell of an odyssey. On the one hand, we were confident the entire time. On the other hand, we were also terrified the entire time. Or I was terrified. Steve, sorry, maybe you don't want to hear this right now. Because it is. I mean, the problem. What makes this kind of work exciting and terrifying is if you don't get through this, you don't have anything. Like, I remember us joking about like, hey, how much could we run on the service processor anyway? Maybe customers want to run their workloads there. Maybe they don't want a CPU. But we'll
call it our ARM data center.
That's our ARM data center, and this is the challenge of this kind of. But it also makes it super exciting and so validating when we actually get all the way through it. So it was a hell of a ride, and I'm sure there are more rides in our future, but that one I think is always going to be special. All right, and Daniel, I saw that you. I don't know if anyone else want to chime in here. Do you want to be mindful of Adam's time and also especially Nathaniel and Eric in Central Time? I know it's late for you both, but
this has been fun.
This has been it's been fun because it booted. That's why it's been fun.
Yeah, we would have had less fun last week.
A lot less fun last week. And I assumed everyone knew that the ending must have been good because we would not be so chipper about talking about what a disaster everything was. But it definitely has been fun to relay this. And yeah, on to the next, on to EVTV. All right. Adam, anything ready to wrap?
Killer. No, Nathaniel, Eric, this has been awesome. Rick, thank you for this. For folks outside of Oxide, even inside Oxide, I get a couple of these pieces often without the explanation to really appreciate it. So this has been awesome. And for future generations of Oxide employees like this, this recording is going to be a great thing to put in the time capsule.
Absolutely. All right. Thanks, everyone. See you next week.
Thanks.
Yep, thank you.